Learn like a pro.
Welcome. Today, we're not just looking at motion. We're going to build a blueprint to really understand it from the ground up. We'll be putting together its most fundamental building blocks, scalars and vectors, to create a complete framework for how things move.
So here's our game plan for this explainer. We'll start with the two basic languages of physics, then see how they help us define a journey. After that, we'll get into the head-to-tail protocol. That's the universal rule for combining vectors, see it in action, and then we'll step back to admire the complete framework we've put together.
Okay, first things first. Before we can build anything, you've got to know your materials, right? In physics, that means mastering the two fundamental languages we use to describe motion, forces, well, pretty much everything. And it's really as simple as this. On one side, you've got a speedometer. It just tells you how fast you're going. That's your magnitude. But then you look at a GPS, right? That tells you how fast and which way you're headed. That's the key difference. One is just how much, and the other is how much and which way. These are the two ways physics describes our world. So let's grab our first building block. It's called a scalar. A scalar is really just a number, a single value. Think about things like mass or temperature or, the speed on your car's dashboard. It just answers the question, how much? And that's it.
All right, now for our second, and arguably more interesting component, the vector. See, a vector isn't complete unless you have both a magnitude and a direction. A great example is force. It's not enough to say you're pushing with 10 newtons of force. I mean, are you pushing up, down, to the left? You have to say which way.
And this table just lays it all out so clearly. On the left, you've got your scalar toolkit, speed, distance, mass, simple numbers. But on the right, you have the vectors. And check out the pairs here. Speed is a scalar, but its partner, velocity, is a vector. This is a super important idea, and it leads us right into our next big distinction.
Okay, so we've got our two languages down. Now let's actually use them. We're going to start with one of the most fundamental ideas in motion, the difference between the actual path you take versus, where you actually end up.
All right, so distance, that's a scalar. It's the total ground you covered on your journey. Every single step, every twist and turn, it's kind of like the step counter on your phone or the odometer in your car. It just racks up the miles. It doesn't care if you were going in circles.
But displacement? That's our vector. And it could not care less about your scenic route. Displacement only cares about one thing, the shortest, straightest line from where you started to where you finished. And of course, it has to tell you the direction of that line.
So if you remember one thing, make it this. Distance is the long, winding road. It's a scalar that tells the whole story of your trip. Displacement is the as the crow flies path. It's a vector that just cares about the final result. One's about the journey, the other's about the destination.
This example is perfect. Look at this track. To get from point P to point R, you have to run along the curve. The total distance you ran? 22 meters. But what's your displacement? Well, it's just the straight line connecting P and R, and that's only 14 meters. See the difference? It can be huge.
Okay, so we've got these vector components, these arrows, but what do we do with them? How do we add them up? Well, for that, we need the instruction manual. And lucky for us, there's one universal rule for this, the head-to-tail protocol. Before we start combining them, let's just make sure we know the parts of a vector arrow. You've got the tail, that's the starting point. You've got the head, the pointing in that shows the direction. And this is crucial. The length of the arrow has to be drawn to a perfect scale to show its magnitude. The method itself is super simple. It's just 3 steps. Step 1, draw your first vector to scale. Step 2, take your second vector and place its tail right on the head of the first one. That's the head-to-tail part. And finally, step 3, you draw one last arrow, the resultant, starting from the tail of the very first vector and ending at the head of the very last one. That's it. You've just added vectors.
Okay, theory time is over. Let's get our hands dirty with some workshop practice. We're going to see how this head-to-tail thing actually works, first in a nice, simple straight line, and then we'll jump into 2 dimensions.
So check this out. We've got a cyclist who rides 200 meters west. Boom, there's our first vector, pointing left. Then they turn right around and go 120 meters east. Now watch this. We draw that second vector starting from the head of the first one. So what's the final result? The total displacement? It's that blue arrow, the one that connects the original start to the final finish. The answer, 80 meters west.
Okay, that's easy enough when you're just going back and forth on a single line. But what happens in the real world?
What happens when forces are pulling in totally different directions, like one pulling you east and another pulling you north at the exact same time?
You know what? We use the exact same procedure. No new rules. Step 1, pick a scale. Let's make it easy. 1 centimeter represents 10 newtons of force. Step 2, draw the 30 Newton horizontal vector. So that's a 3 centimeter line. Step 3, from the head of that first vector, we draw our 20 Newton vertical one. That'll be 2 centimeters long, pointing up. And finally, we just draw our resultant to close that triangle.
And here comes the magic. First, you just take a ruler and measure the length of that resultant arrow. Let's say it comes out to 3.6 centimeters. Now, using our scale, we just multiply that by 10, and we get our final magnitude, 36 newtons. But wait, we're not done yet, are we?
Exactly, because a vector always needs a direction. So we pull out a protractor, we line it up, and we measure that angle from the horizontal. And it looks like we get 33.7 degrees. Now our answer is complete. The resultant force is 36 newtons at an angle of 33.7 degrees.
All right, let's take a step back for a second and just look at what we've built. We've assembled a complete blueprint, a schematic that ties all these ideas together into one powerful system. This is it, our whole framework on one slide. You start with any physical quantity. First question, is it a scalar or a vector? If it's a vector, you know exactly what to do. Use a scale diagram, apply the head-to-tail rule, and find the resultant. This is our master plan. It's a reliable process that can turn any messy-looking physics problem about motion into a simple, solvable geometry puzzle.
You know, the biggest takeaway here is that what looks complex is often just a bunch of simple things put together. With this blueprint, you can break down any kind of motion, no matter how chaotic it seems. So the question isn't just about what we did today, it's about what you can do with this now. Are you going to deconstruct the forces on a bridge, the trajectory of a satellite? Once you have the framework, you really do have the power to map out the mechanics of the entire world around you.